Hello all. Today we discuss modeling a control system. The next part is the generator. So first our topic is today the generator. We're modeling the generator parameter, and first part is separately excited DC generator. Okay, this is our first topic, DC generator. Okay, now this is our first topic in today, separately excited. This is a DC generator. Okay, the transfer function of a separately excited DC generator related the input field winding voltage VF and the induced voltage developed across the armature, okay, derived in this lecture. So now first of all, what is a circuit diagram? The equivalent circuit diagram is look like a this input voltage, these RF, these are field current IF, these are inductance L, and here the generator G, and here from here the output equals to E. E is the output. Okay. Now one thing should be remembered, that this circuit diagram, the resistance and the inductance of the field winding are RF and LF respectively. The generator being driven at a constant speed and is operating in the linear portion of the magnetizing characteristics. So that's why here the current IF flowing in the field winding produce a flux in the generator, which is in turn to induce the proportional voltage at the armature terminals. The relationship between voltage E, that is this voltage E, and the field current IF given by the magnetization characteristics. Some characteristics are plotted here. If we plot the field current in the x-axis and EMF developed, then this is a linear part and this is the saturation part. And now if we take the delta, so the delta of IF, that is from here one constant is coming out, which is known as generator constant, that is Kg, which is equals to delta E by delta IF. Okay, so these are very important. So this is a linear part when we take the delta. Now one thing should be remembered, the induced voltage small e is related to the field current, that is E is proportional to here IF first, and next E is equals to Kg into IF. This Kg equals to basically generator constant. Okay, now we first find out the relational equation. So from this input side, we see that from the Kirchhoff's voltage law apply, VF equal to this drop plus this drop. So therefore IF into RF plus LF into DIF by dt is the first KVL equation. And next, at that the output, we already see that this is a Kg into IF. Okay, so now the Laplace equivalent equation is VFS into RF into IFS plus S into LF into IFS, and here ES equals to basically Kg into IFS. Okay, this is very important equation. Now if we modeling the block diagram, so now first this is input VFS. So here transfer function is equals to 1 by, yes, right, RF plus S into LF. And what is the output? The output is equal to field current. Okay, and now what is the relationship between field current and the EMF? There some parameter is related, multiplied by Kg, and we get the EMF voltage ES. So this is a block diagram of separately excited DC generators. Okay, so this is very important. Now we talk about the modeling parameter of separately excited DC generator connected to the load resistance. Okay, the load means the electrical load is connected. Now our second topic is separately excited DC GN means generator connected to RL, that means load resistance. Okay, this is our second topic today. So now the equivalent diagram is look this equivalent diagram. Again, these are field resistance, these are field inductance. Here we apply input voltage VF, here the generator G and the armature resistance, and here RL is a load resistance and the output equals to, say, for Vt. Okay, now here develop EMF E. So this is a DC generator connected to the load. Now see that first of all, this Vt is basically equals to this E minus IL into Ra. This IL because here the load current is IL. Okay, first of all, see that this is the equation because this is a load current expression. Okay, and this IL is basically Vt by RL. So now what is the Laplace equation? Vts equals to Es minus Ra into ILS. And what is the relationship between them? ILS equals to Vts by RL. So now these are Vt, basically Vt. So now from the block diagrammatically approach, first we apply here Es, our source input EMF, and here a comparator block, and from here Ra into Ls is coming. So here the parameter is Ra into ILS. So this is an output. Okay, so now from here coming out one parameter is Ra, and here these are very important, this is 1 by RL. Okay, so now from here we getting ILS, and here the constant block 1, and this is the TS, because here voltage equals to Es minus Ra into ILS. So now this block is multiplied by into 1, say for example. So this is a unit gain and getting the output voltage Vt. So now from Vt, first of all you 1 by RL to get Is here. Okay, this is very easy, and then multiplied by armature resistance Ra, because to get this expression, because Ra is multiplied. So Ra and RL both are in the feedback system. Okay, is it okay? Yeah, right. So this is a block diagram of DC generator connected to the load. Okay, this is very, very important. And this is the two topic we discussed in this lecture. Okay, so now we discuss about the concept of next DC tachogenerator. Next our topic is DC tachogenerator. So now this is first the diagram of DC tachogenerator. This is north and south pole, and here the angular rotation of speed omega, and here output is equals to E, this output. Now this is a figure of this tachogenerator used to convert a rotational speed into a proportional DC voltage. It uses permanent magnet for producing magnetic field. This is the permanent magnet, 2 poles, and the tachogenerator is coupled to a shaft of which speed is to be measured. As the magnetic flux is constant due to use of permanent magnet, then the induced voltage at the terminal of the armature is proportional to the shaft speed, and the polarity depends on the direction of the rotation. So therefore, first of all, we write that the developed EMF is proportional to omega. Therefore, E equals to KT into omega, where KT is a tachogenerator constant, or known as TG, where KTG is a tachogenerator constant expressed in voltage per radian per second. And now if we take the Laplace transform, then ES equals to KTG into omega s, the Laplacian domain. So therefore, for ES by omega s is basically the constant, tachogenerator constant. So therefore you see that A DC tachogenerator can also be used for AC system by using modulator to convert DC voltage signal into AC voltage. Okay, so this is very interesting. Okay, because here some constant parameter kdg, but for the DC tachogenerator, and this is also used for the AC system by using the modulator to convert the DC voltage signal into the AC voltage signal. Okay, so modulator concept is very much easy. So now we see our next topic is to talk about AC generator concept, AC tachogenerator concept. Okay, AC tachogeneration. Now AC tachogenerator is used to convert a rotational speed into proportional to the AC voltage as work on the principle of induction generator. So now see that this is the circuit diagram. Here this is a rotational speed of omega. This is a rotor. This is one rotor, and this is a reference winding. This is a reference winding, and this is output. From here we take the output E, and this is the output winding. The two winding are okay. So now the tachogenerator is coupled to shaft of which speed to be measured, and the reference winding is supplied by a reference voltage, and the output voltage E, that means this E output voltage from here, the taken the output E is induced across the output winding. So basically this so now here also E is proportional to omega, so therefore E equals to again kTg as we seen in the DC tachogenerator. So now we see that we take the Laplace transform. Now omega s. Okay, so now you see that again here is this is a block. The input is omega and the output is basically es. So basically the output voltage is proportional to the angular speed. Okay, so now AC tachogenerator can also be used on DC system by using phase sensitive rectifier. Okay, so now from DC tachogenerator to AC tachogenerator we used basically modulator, and from AC tachogenerator to DC tachogenerator we used basically phase sensitive rectifier. Okay, because you already know that AC to DC conversion, there is the concept of rectifier is coming out. Okay, so that's why it's very important. Okay, next one is we discuss about the topic just a minute. Okay, now we discuss about some problem related to modeling a control system. So find out the transfer function relating the displacement y and x for the mechanical system shown by the circuit. Sorry, not a circuit. Sorry, I'm sorry. This is basically a mechanical diagram. So now this is a mechanical diagram where F1 and F2 to damper, and this is a spring constant K. This is fixed by this terminal. This is a B. Okay, and here the point A, and here the displacement direction is the force acting on it. So now the displacement equal to x, and from here the displacement is y, the direction of the displacement. This is the direction of the displacement. Okay, displacement. So now this is a mechanical circuit diagram. From the mechanical circuit diagram, the equation of the system. So first of all, there are basically two equations are represent for this y and x. So for y we write f2 dy by dt. So first of all, this is a viscous coefficient. This is a ky plus f1. This is a d by dt y minus x. Okay, this is a resultant because y minus x, but this force with respect to this. Okay, so now if we take for this equation, so now for f1 d by dt of this is basically x minus y. Okay, because this respect to this, so that is equals to force ft, because there is no force is applied. Okay, because from the these are coming from the Newton's second law equation. Okay, assuming all initial condition equals to 0. So if we transform this equation in the Laplacian domain, then we get f2 into sys plus k into ys plus f1s in a bracket ys minus xs equal to 0. Okay. Okay. So basically the thing is that, so from here ys by xs is basically just simple the transfer function f1 plus f2 f1 f2 into s plus capital K. So now this is the transfer function for this system. Okay, so now this is the transfer function for this system. This is an example of modeling of the modeling a control system. So now there are another problem. This is the homework. Okay, now this is a spring constant k1 and this is a m1, and here the force, sorry, viscous coefficient f3, and here mass m2, and this is a spring constant k2 fixed by this digit, and this is x1, this is x2, and force is applied here. This is a direction of displacement. Okay, this is f3, and one thing should be remembered for the mass m1 there is constant f1 and this is f2. Okay, the f1 f2. Okay, that's all for today. Thank you.